Good. All right. Let me just, I haven't looked at any of your tests yet. I just this morning got the test from the high school students, so I wanted to grade them all together so I could be more consistent in how I grade them. It also gave me a retreat from grading for a day. Anyway, let me pass this thing out, the handout, and then we don't want to be too idle. This homework here is, however, is not due until Monday, the 11th. So that's something.
Monday.
Yeah, Monday. It's going to be homework 11 due on 11/11. How can I? All right. Here's the homework. Here's a couple of handouts. Well, let's see what Kyle is going to join us today. If we could throw this pair down that way. Okay. You can tell you 5 minutes will also be posted online. I usually email this as the soft copy of this. Okay, I'm working on it. I thought about that, but then point is taken. All right. Algebra stuff away. And chapter 8 stuff. All right. All right. Okay. Well, we'll all be glad to hear that we're putting theories to bed for a while until the final. All right. So we're getting back to some more traditional calculus stuff. All right, with these next couple, with the next several. In fact, for the rest of the semester. Let's put it that way. Okay, so we're jumping back to chapter 8. We're going to be covering just the first 3 sections in chapter 8. So we're going to start here with section 8.1, and this is calculating something that's called arc length. All right, and basically arc length is just a fancy term for the length of a curve. The length of a curve from, say, point A to point B. So we have a curve, we have a point here, we have a point here, and what we're going to figure out here is what is the length of that line in between those 2 points. All right? The way we do this, let me get this up here, and I need to change your stuff here. All right. Okay, basically, notice this blue line here. This is our curve, all right? And what we do is we just divide up this curve into using points, equally distant points, into straight lines that approximate the curve, all right? So here we have several points along the x-axis, and we're then connecting the points on the curve. So we've got a bunch of straight lines that are pretty close to the curve itself, all right? And what we do then is we just keep creating more and more of these points along the x-axis that are equally distant from each other to get a better and better and better approximation of the length of the curve. Because the length of the curve is ultimately going to be the limit of the sum of these lengths of these straight lines, okay? So we can just take between any two of these points here, say here's our curve here, here's two of the points, we then go divide more and more. Here we're dividing it again by 2, here we're dividing it by 3, here we're dividing it by 4, to get closer and closer approximations of those straight lines to the actual curve, all right? So we can figure out the length of each one of those straight lines. So let's escape out of that and go back to this. Right? Okay, and let me get this down. All right. Oops, and I think I better make this a little bit bigger for some of those people that are trying to. Let's do this. And let's, oops. Okay, come on. All right, let's do that. There we go. Okay. All right. So therefore, the length of the curve is going to be the limit as these numbers of lines go to infinity, so n goes to infinity, of the sum from I equal 1 to n of these lengths. And we'll just call this point P sub I minus 1 to point P sub I. This is the length of each small straight line segment. All right. Okay, well, we can figure out from using the Pythagorean theorem how to get the length of one of these segments. All right, so here we have P sub I, one of the points on the line. Here we have another one, P sub I plus 1. We're joining those 2 points with a straight line to approximate the length of the curve. Well, I can just create a nice right triangle here. This one length is going to be delta y, the change in y. This other one is going to be delta x, the change in x. So therefore, this length here on the hypotenuse is going to be the square root of delta x squared plus delta y squared, using Pythagorean theorem. Okay. Now, we're going to digress with one thing that you may or may not remember from Calc 1, and that was called the mean value theorem. Does anybody remember even that name? Okay, Nikisha, good. Okay, good. Does anybody remember what it said?
Not like the literal definition.
Even the general idea of what it said?
Taking the sum of 2 points and dividing by the sum of 2 points, dividing by 2, being the average.
Well, it does have to do with the difference. Okay, it does have to do with the difference. I won't put you on the spot anymore here. Let me just put down what the mean value theorem is. If we have a function and we just want to look at continuous functions. So say it's continuous from x equal a through x equal b, including the intervals. And in the middle there, it's differentiable, so we have a derivative. And it's differentiable, and we really only want to make sure that it's differentiable on in the section between the 2 endpoints, so I don't have to include the 2 endpoints there. then what happens is this. Then there is a C that's between the A and B points, between A and B. There is a C between the A and the B, such that we have this. The function at the one endpoint, f of b, minus the function value at the other endpoint, f of a, is equal to the derivative of that function at that value c times the difference of the two x values times b minus a. Okay, that's the mean value theorem. So the difference in the y's is equal to some derivative times the difference in the x's. Of course, another way of saying this, the difference of the two function values, that's really our delta y. So delta y is equal to f prime of c times delta x. All right. So let's look at one of these little line segments here. So again, let's go back, let's look at a line segment here and here that's joining, straight line joining, say x sub I, y sub I, and this is x sub I plus 1, y sub I plus 1. And let's say that our curve then, I'll put the curve as kind of a dotted line here. So our curve is joining those 2 points, of course, and we have that straight line. What this mean value theorem says is this, that somewhere between xi and xi plus 1, there's a value of x such that the derivative, when we do the derivative, the tangent line is parallel to the line joining the 2 points. So basically we have this. We have here is our delta y, here is our delta x, and basically delta y is equal to this derivative value. Let's just call it something like this. Put a little tilde or something over the x times the delta x. All right. Okay. Because we can see here that delta y, if we divide delta y divided by delta x to get the slope, that's going to be the same as the value of this derivative here in the middle somewhere. All right. So what this does now is this gives us, in our delta y and delta x formula, this gives us a derivative. So therefore, we can say this, that delta x squared plus delta y squared, that can now be rewritten as, well, I'll put delta x squared in still, but in place of delta y, I'm going to use this new formula right up here, plus, I'm going to square this, so it's going to be the derivative at some middle point there, and that's going to be squared, and then my delta x also has to be squared, because I have to square that whole delta y. So I get something like this. All right. Now what I can do with this, so this is the length of the straight line. It equals that. Now, what I can do then with this is I can divide on the underneath the radical, I can divide both of the terms by x squared, but if I do that, I have to multiply on the outside of the radical by just delta x, all right? So if I divide by delta x squared and I multiply on the outside by delta x, I'll still have the same thing. So we're going to have this then. So now I'm going to have a 1 here when I divide by delta x squared. And then here, I'm going to just have my derivative squared. That's going to stick around. But my delta x squared is going to go away there. But then on the outside, I have to multiply by a delta x. The 1 is from delta x squared divided by delta x squared. I'm dividing both of the terms under the radical by delta x squared. So both of the x squareds here, and here will both go to a 1. But at the same time, Jordan, I then have to multiply on the outside by delta x. Otherwise, I change the whole thing. Right? All right, so this is all leading up to my formula. All right. So therefore, the length of my curve, now we're at the length of the curve, this is going to be the limit as my intervals go to infinity of the length of my individual straight lines. So I'm going to put limit of 1 plus f prime of x tilde x, and that's all squared, times delta x. Now, this should, from Calc 1, be reminiscent of how you first looked at an integral, where you took those integrals, getting smaller and smaller, summing them up, that gives you an integral. So what this limit equals is this. The integral from x equal a to x equal b of the square root of 1 plus the derivative of the function squared dx. And this is the length of the curve between x equal a and x equal b, right here. Okay. So this is our length, or arc length. We could also then call this arc length. All right. So let's work with this formula then here to do an example. The first example actually involves a little bit of, we have to use substitution with it, but it's not too bad. So here it is. Let me try to keep this up here. Let me fold this so we have this up here on the screen, this formula. All right. Okay, so the example is this. Find the length of the curve or we could call this the arc length. And the curve is y squared equal to x cubed, so that's kind of unusual, between x equals 1 and x equals 4, and we want to do it for y bigger than 0. So let me just give you a very rough sketch of what this particular curve looks like. Here's our y and x-axis. This curve above the x-axis curves up like this, and then it has this break right here, and below the x-axis it goes down like this. All right. Yes, Jenna?
I just had a question. When you took that formula and then you put it into the integral, why did you get rid of the delta?
This is from Calc 1. When you take that limit, the delta x gets replaced with a dx. Okay? When you were calculating area under a curve in Calc 1, you were summing up a function value times delta x and remember those delta x's got smaller and smaller, it's equal to an integral with dx in it. The delta x becomes a dx. Just like, okay, so basically that's the answer there. All right, so here we're looking at, okay, x equal 1 and x equal 4. So we're trying to calculate that length right there, where y is bigger than 0. So first of all, we are going to have to get f prime. Now, another way of writing this arc length formula is this: a to b of the square root of 1 plus. Now, we know that another way to write f prime is dy dx. All right, so this is just another way of writing the very same thing. dy dx in parentheses squared times the dx. All right, just changing what this is called Leibniz notation, if you're interested in that, Leibniz notation. So we all know we can represent a derivative one of two ways, with the prime or with dy dx. All right, so the first thing we need to get here is we need to get dy dx. So let's solve for y, and we take the square root of both sides, and so y is equal to the square root of x to the third power, just taking the square root, and the square root of x to the third power, what's the exponent that I'll have? 3 halves. 3 on top, the root on the bottom. So here's y is equal to x to the 3 halves power. Okay, so let's get the derivative. dy dx is 3 halves times x to the 1 half power. Okay. All right. So now let's plug this in here to our integral here. So we're going to have, let's first of all just look at this radical. So now we're going to have radical 1 plus, in parentheses, 3 halves x to the 1 half power, and I have to square that derivative, all right? So let's see what this gives us. This gives us the square root of 1 plus, now what am I going to have for that square there? Exactly. Got to square the 3 halves, that's going to give me 9 over 4. And then when we square x to the 1 half power, that's just x. So that's what we have. All right. So this is what our problem becomes then. Okay, our a is 1, our b is 4, so I plug in those two endpoints for our integral. And then we have the square root of 1 plus 9/4 x dx. All right? So now it becomes a problem of calculating the value of that definite integral. So what are we going to do here with this? Absolutely. We're going to do a u substitution. We're going to let u equal what's under the radical, 1 plus 9 over 4x. All right? And so our du becomes 9/4 dx. And since we've got a definite integral here, I'm going to go ahead and change my limits of integration now, and so that I can just keep with the u. So here, when x is equal to 1, my u is going to be equal to what? 1 plus 9/4, right? Which is, when we combine them together, is 13 over 4, right? And now for the top one, when my x is equal to 4, I'm going to have 1 plus 9/4 times 4, so my u is going to be equal to a 10. All right. Okay, so let's get rid of that, and let's continue then. So now we have new limits of integration, and we have a u here, so let's substitute. So now we're going to go from 13 over 4 to 10, and let's see, my dx, oh here, I need to put this here. If du is equal to 9/4 dx, then dx is equal to 4/9 du, just by multiplying both sides by 4/9. So I'm going to replace my dx with 4/9 du, and then my square root is just going to become the square root of u, or let's just use exponent notation, u to the 1/2 power. Okay, so now we just have a simple integral to get. So the antiderivative, we're going to keep the 4/9. It's going to be u to the 3/2 power divided by 3/2, and we're going to go from 13/4 to 10. And let's simplify that fraction in the denominator. That's going to be 4/9 times 2/3 times the reciprocal of u to the 3/2 from 13/4 to a positive 10. Okay. Well, let's simplify that. What do we have there? 8/27. Yeah, nothing cancels out of that. So we have 8/27, and now let's plug in my u values here. So we're going to have the top value is 10, and that's to the 3/2 power, minus, and my bottom value is 13/4, and that's also going to be to the 3/2 power. Now you could, I don't care about it. If you can do more simplification with this, because what 4 to the 3/2 power equal in the denominator? It equals 8. The square root of 4, which is 2, 2 to the 3rd power is 8. So you could do some further simplification with that. I'm fine with it just as it is here. That's okay with me. So this is our length of our curve. It's not a nice, simple number, but that's what we get, okay, using the formula. Any question on just the first example? It all centers around the formula here. Now, what happens sometimes is our curve sometimes is written as a function of y as a function of x. So this can happen sometimes. Sometimes a curve may be written as x equaling a function of y. And that's rather than y equaling a function of x. Probably one of the easiest examples to give you of this would be something like x equaling y squared. This is going to be basically a sideward tilting parabola. Okay, here's our y-axis, our x-axis. It's going to curve like this, and it's going to curve like that. That's what our curve would look like. Okay. Versus the way we're usually used to seeing things, y equal to x squared, where the curve is then drawn like that, okay? Now, if our curve is given like this, where we have x in terms of y, what we have to do to our formula is basically switch the x's and the y's, okay? So, in this case, switch the x's and the y's in our formula, and to get this. So, now we can say the length of the curve between, now we're going to look at two different y values, say between y equals c and y equals d would be something like this. Okay, we have our integral. Here we're going to have our lower y value, our bigger y value, and then here we're going to have 1 plus. Now instead of having dy dx, we're going to have dx dy squared, and instead of having dx, we're going to have dy. All right. So compare this with the other formula. The other formula was from a to b of the square root of 1 plus dy dx squared dx. All right. So it's just switching the x's and the y's. Okay. Now, if another way of writing this one is by using the other notation, if x is equal to, say, g of y, I could write that top formula as this: y going from c to d of 1 square root of 1 plus g prime of y squared dy. They're both equivalent to each other. Okay. So I want to now look at a case where the curve is defined in terms of y and get the arc length. Okay, just using the second formula. Anybody have a question? I'm just flipping the x's and the y's there. All right. Okay, so let's look at this example here. Say we're given x equal to y squared, and we're asked to find the arc length, or the length of the curve, from 0, 0 to 1, comma 1. All right. So what we're talking about here, just drawing this, x equals y squared is going to look something like this. All right? And we're talking about going from the origin here to the point 1, comma 1, and getting that length right there. Okay. So we're going to then, so we have x equals y squared. So now we're going to get dx dy, and that's going to equal what? 2y. Right. Okay. And then we're just going to plug into our formula here. So our bottom value of y is 0. Our top value of y is 1. So these are the y values. Now in this case, they're the same, but it would be the y values. Yeah, Jenna? No. Dx dy is equal to 2y. If you're going to do that, then we're talking about dx equals 2y dy by multiplying both sides by dy. All right? But here we're just finding the derivative with respect to y, and then it's just equal to 2y. So let's plug this in, so that's going to be the square root of 1 plus our derivative squared, so 2y in parentheses squared, and then we have a dy at the end there. Okay, so this is going to be what? 0 to 1 of the square root of 1 plus 4y squared dy. Okay. This ought to harken back then. Okay, what are we going to do here with this? How are we going to handle this integral? 1 square root of 1, yes, it's still alive and well. How are we going to handle this? Yes. And what kind of substitution? The tangent, right. We're going to do a trig substitution, so that stuff is not going to be forgotten. It's alive and well. Remember, with trig substitution, if we have a plus here, That should be your clue to use the tangent, all right? So basically, Mitchell, then what would be, can you give me what my equation would be here for my substitution?
Y equals 1/2 tangent theta.
Okay, y equals 1/2 tangent theta. Another way that I would put that initially is that 2y equals tangent theta, which is the same thing, comes down to the same thing. We want to take that 2y, which is the square root of that one term, and we want to set that equal to the tangent of theta, all right? And equivalently then, if we just divide by 2, set y equal to 1/2 the tangent of theta. And then we get our dy. dy then is 1/2. The derivative of the tangent is the secant squared. And then we have our d theta. Okay. All right. I'm going to leave out for the moment the limits of integration. So let's see, what is this going to become then? This is going to become what under the integral then? 1 plus 4y squared is going to transform into what? Right, 1 plus tangent squared of theta. And then our dy, I need to replace our dy with, let's put the 1/2 in front, and then we have still a secant squared theta d theta. All right. So then this can be further simplified because 1 plus the tangent squared is equal to the secant squared, right? So this is 1/2 of the secant of theta times the secant squared of theta, which is 1/2 secant cubed of theta d theta, all right? Before we look at the antiderivative of this, let's look at our limits of integration, because when you do substitution with a definite integral, it's the best thing to do is just change your limits of integration, and then you don't have to go back to the original variable. Okay. So we have y is equal to 1/2 tangent of theta. Okay, so our first value for y is 0. So when y is equal to 0, we're going to have tangent of theta has to also equal 0, right? So what would be that theta angle value? 0, right. Tangent of 0 is 0, right? So therefore, theta is equal to 0. And then let's look at the other one. The other one we have is when y is equal to 1, we have tangent of theta is equal to, wait a minute. We have 1/2 the tangent of theta is equal to 1. So that means tangent of theta is equal to the number 2. All right, so that's not in one of our nice special triangles. So basically, this theta angle can be written as the inverse, the tan or the arctan of the number 2. Because we don't have a nice triangle to tell us an answer for this. All right. So let's see what this comes out to be then. We're going to change those limits of integration. So the first one now is going to be a 0. And the upper limit is going to be the tan inverse of 2. All right. And then the rest of our integral is 1/2 secant to the 3rd power theta d theta. Now, I don't expect you guys to remember the antiderivative of the secant cubed. We did do it as an exercise in class, but it's certainly not something I expect just to be on the tip of your tongue. So this is the antiderivative of this. We certainly want to keep the 1/2 that we have here. The antiderivative of the secant cubed is this. So in the brackets here, it's 1/2 times this, times, and then it's times another parentheses, the secant of theta, tangent of theta, plus the natural log of the secant of theta plus the tangent of theta. So I know that that was the first thing that you were going to say is what the antiderivative is. Okay, so it's this whole big formula here where the 1/2 is multiplying both of those terms. And so this antiderivative then is going from 0 to the tan inverse of the number 2. All right. Okay. Now, notice what we have to plug in here. We have to figure out what the secant is of this angle. We've got to figure out what the tangent is of that angle. How can we do that? Yeah, draw a triangle. Exactly. Let's draw a little triangle, a little right triangle here. And let's put in the corner here, let's call it, let's give it a name actually. Let's call it alpha. You can call it anything you want to. And this angle that we're putting in here is the tan inverse of 2. That means that the tangent of this alpha is equal to 2, right? So what can I put in for this leg and this leg to give me a tangent of 2? Yeah, 2 here and 1 here, exactly. That gives me a tangent of 2 for that angle. And then I use Pythagorean theorem to get my hypotenuse, which is going to be 1 plus 2 squared, which is 5. So my hypotenuse here is going to be the square root of 5. So we have to draw a little triangle. Okay, all right, you're with me there? That okay. Okay, so let's go see what we got here. Okay, first of all, 1/2 times 1/2 is 1/4. So let's get that out of the way. And actually, well, now let's do some parentheses. So the first thing we have to do is the secant of this of the tangent of the arctan of 2. So we have to do the secant of this angle alpha. All right? So what's that going to be? Square root of 5, right? It's the reciprocal of the cosine. So here, for the secant of that tan inverse of 2, I'm going to put the square root of 5, and then I multiply it by the tangent. Well, the tangent is just going to be 2 over 1 or 2, all right? So this is the tangent of the alpha. And then I have to put a plus sign here, and then I do a natural log. And then I fill in the secant of this angle, which again is the square root of 5. But now I add plus the tangent, which is the number 2. And I don't have to use absolute values because those are both positive numbers. And then I close my parentheses. So that's from the whole top part of plugging in the tan inverse of 2. Then my bottom part is I have a minus 1/4. And now I plug in my 0. Okay, so what's the secant of 0? 1. Cosine of 0 is 1. Secant is just the reciprocal of that. So that's a 1. And the tangent of 0, however, is 0. So that kind of wipes the 1 out. And then we have the plus ln. And it's going to be the secant plus the tangent, so that's going to be 1 plus 0 after the natural log. Okay. So look at what we have down here. We have 1 times 0, that's a 0. And we have the natural log of just the number 1. And what does that equal? 0. So this whole bottom part is all a 0. So all we're left with is the top part. So this is our answer here. 1/4 times the square root of 5 times 2 plus the natural log of the square root of 5 plus 2, like that. And yep, that's fine. Good enough. All right. So again, no simple, nice whole number, anything like that. Yes, Jenna?
Would we be required to find, like, on the integral of secant cube? Because I don't really remember, I don't know how you got it.
Okay. Something like the integral of a secant cube, which I'm not going to ask that you remember that antiderivative. If ever on an exam, I would put what the formula is. Does that answer your question? Yeah. All right. I may seem unreasonable sometimes, but I'm not that. All right. Okay. Now, I think we can look at this one thing and then just take a break here. What we're looking at next in this is we're going to measure the arc length, or the length of the curve, from a certain starting point to any other point on the curve. All right. So let me just draw a picture of what we're talking about here. So say we have a curve like this, and say right here is the starting point that you're given, or that we want, all right? So let's say that this is where x is equal to the number a. So the coordinates of this starting point would be a, and this is f of x right here. So how would I represent the y coordinate of this starting point? Well, that's one way, but I'm going for something else, so well, f of a, right. The point here on the curve is the y coordinate is the function value, all right? So the y coordinate would be f of a. That's the thing I was looking for, okay? So that should be something kind of, the y coordinate on a graph is the function value, all right? So that's our starting point. And we want to go to any other point on the graph. So and by the way, let's call this starting point P naught, all right? And say we want to go to any other point here. So the coordinates of this point would be, any value of, let's just call it x, and the y value would be f of x, all right? So it's a variable, any other point, and we'll call this point Q, all right? So we want to find this distance, this length of this curve here between those 2 points. We're going to call this f of x. We're going to call that the distance from the starting point. From the starting point. Actually, let's cancel out distance and call this the curve length, or the arc length, from the starting point to Q, all right, to the variable point. Okay, so therefore we just used our formula. S of x then is going to be that integral from our x value is a for the starting point. Our x value for the other point, though, is just plain old x, all right? And then we have the square root. Now, to avoid confusion, what we normally do with this is we put in a dummy what's called a dummy variable. Instead of calling our variable inside the integral x, we can call it t or some other variable name. So we can call this 1, so the formula is 1 plus the derivative of our function, but we're just going to use a dummy variable t. Remember, we have to square that the derivative, and then it's dt. So this is just, t is our dummy variable. Did you guys hear that term or see that term in Calc 1 at all? Dummy variable? Dennis going, no, haven't. The only dummy was the teacher. Okay, so that is something that you do see sometimes. It's just this dummy variable. It's kind of like a placeholder. Cassandra, sorry. I keep doing that. I apologize. All right. Okay. This thing has a name. Notice it's a function of x. Because x can vary. This is called the arc length function. All right. So before we get break, I want to just get this other point in here. So we have this arc length function here, that s of x is equal to this integral. Now, in Calc 1, you learned that there were two forms of the fundamental theorem of calculus. And one of them is this. When we take the derivative of this s, this integral, we're going to come up with what is inside the integral evaluated at that top variable, x. So this is from one of the fundamental theorems of calculus. That now we can say from this formula right here, this integral, we can say that the derivative of this s function with respect to x is equal to what's on the inside of that integral. So it's going to equal the square root of 1 plus f prime. But now I can plug in that x that's right up on top there. That whole derivative is squared, f prime of x squared, like that. Okay. So we have this formula. Another way I can write this with the other notation, the Leibniz notation, is 1 plus, instead of writing f prime, I can write dy dx squared, like that, under the radical. Now, if I multiply both sides of this equation by dx, multiply both sides by dx, and that's something we can do. The left side then is going to become just ds. The right side is going to become 1 plus dy dx squared times dx, like that. Now let me bring that dx under the radical. To bring it under the radical, what do I have to do to it? I have to square it, right. So this is equal, so ds is equal to the square root of, where are we here? Well, actually, okay, well, I'll go on and do this. Is equal to the square root of dx squared plus dy squared. I really didn't want to go here, and so you can just, that's fine, that's a true statement, but that's not really what I'm interested in. This is what I'm interested in right here. So let me rewrite this just to make sure we're clear. ds then is equal to square root of 1 plus dy dx squared times the dx. Now, if we had our curve written as x in terms of y, if the curve were written as x in terms of y, all right, in other words, x equaling, say, g of y, then we would have the similar thing here. Then we would have dx dy equals the square root. I just interchanged the x's and y's, so this would be the square root of 1 plus dx over dy squared times just that, all right? And so I would then, if I multiply both sides by dy, I get this formula. The ds can be rewritten as square root of 1 plus dx dy squared times dy. All right. If you look here at this, although we certainly haven't gotten to this section yet, if you look at this handout here, this area of surface of revolution, at the very top of it here, we have these two formulas for dx. It can be written, it depends on whether our curve is written as y as a function of x or x as a function of y. So I've got both of these formulas written up here for ds. And so that's, we'll be using these formulas when we get to the next section, 8.2. All right. Why don't we take a 5-minute break, come back around 10 after, and we'll do one other problem here in this section. Is this stuff that we're now doing a series of? I don't do stuff for you guys. I mean, I know like half of the course was a lot of review. Tree substitution probably was new also. Yeah. So that's okay, yeah. So what do they have in high school? Is there something actually going on, or is everybody have a day off?
We have a day off. We have parent teacher conferences, so the teachers they like after school 4 hours. So they have to get a day back.
Okay.
Halloween break.
Yeah, it's kind of, the terrible thing about the fall semester is that we go a really long time. Everybody's getting burnt out. It happens to be, I'm sure the break has nothing to do with all things today. But yeah, right. But anyway, but we don't have a break until Thanksgiving. And Uncle has the whole week off for Thanksgiving. You guys, yeah, like the students, they caved in to the reality of the fact that a lot of the students just aren't there anyway.
Doesn't fit because of the fact that the next week is like final. It's
Well,
like,
no, actually not. The next week is the last week of class. and then you have finals after that. Right. Now you guys, you get Wednesday off.
Not really.
Don't you?
Yeah. We get like Wednesday off.
Yeah, you get Wednesday, of course, Thursday, and you get a Friday off. St. Louis Community College, though, is so generous that they want us
Jenna. No, I'm not, thanks for the suggestion. But knowing me, I'm not gonna cancel class. The drudge, the taskmaster that I am, I'm not.
Well, he's got an experiment that day too, he's got chemistry.
Oh, you have secret for chemistry, huh? At Merrimack, okay, yeah. So you're gonna be working anyway, so you might as well come on over here.
We checked.
Yeah, so there's, I don't know.
Maybe one of these days they'll add on at least a Wednesday, but not this semester. And I will send out an email to you guys when I have the test scores reported, so that you can then look what your score is. What's the okay? I'm gonna just keep picking on you here, Mitchell. What was the consensus over the others?
What that will be a whole, the initial,
Yeah. Right. There were a few things in there that just must be.
I try to underline that to make a difference from a theory.
I felt so stupid, I forgot to do some, like, and then after, I'm like, oh my god.
The sum?
Some, I forgot.
For a geometric theory.
Yeah.
Oh, yeah, A over 1 minus R. Yeah.
I was like, Amy, I don't remember, she's like, it's that, I was like, oh my god, that's so easy, I totally forgot that I can.
There's a lot of stuff to remember. I know. All right. The last thing I want to do then on this section is just to calculate an arc length function. So here we have find the arc length function f of x for the function f of x equal to x squared minus 1/8 natural log of x. And so I have to give a starting point with p naught equal to 1, 1 as our starting point. Okay. And of course you see when you plug in 1 here for x, we get 1 squared minus 1/8 times 0. ln of 1 is 0. So that is our starting point there. Okay, so the first thing we need to do then is to calculate f prime of x as our first thing. So f prime of x then is going to be 2x minus 1 over 8 times 1 over x, or 2x minus 1 over 8x. Okay. All right. And then we know we have to square this, so why don't we get this out of the way also? So let's square this. So we're squaring 2x minus 1 over 8x, and we have to multiply it by itself. So I'm just going to write it out like this, and you basically FOIL it out, okay? And when we FOIL this thing out, we get 4x for the first two terms. Now, the two middle terms, the middle and the outer terms, those are going to be what? The two middle terms is going to, when I multiply them together, is minus what? Minus 1/4. The x's cancel out. The same thing with the two outer terms. When I multiply them together, I also get a minus 1/4. And then let's multiply the two last terms together, and I get a double negative gives me a positive 1/64x squared. So let's just combine the minus 1/4 here. So I get 4x squared minus 2/4, or minus 1/2, plus 1/64x squared. All right. So we had to do a little work to get the square of the derivative, and this is going to be the kind of thing you're going to see on some of the homework problems that I assigned here for this. So now we have to look, okay, let's just kind of do this incrementally here. Now we have to figure out what the square root of 1 plus the square of this derivative is. All right? Yeah.
This supposed to be 1/4 x and 1/2 x, or you think that way?
The x's cancel out. Because notice we have an x on top and an x on the bottom. Is that what you're saying?
Yeah.
Yeah, see, the x's cancel out for those middle and outer terms to just give us a negative 1/4. All right. Now, let's figure out what this is. Now, okay, so we have basically 1 plus this whole thing that we figured out. 1/64x squared. All right, so what we need to do, of course, is we need to combine the 1 and the negative 1/2 together. And let's see what we come up with here. So let's write it like this. I'm going to lead off with the 4x squared. Now let's combine 1 minus 1/2. That's going to give me a positive 1/2. And then I have my 1/64x squared. Now, guess what's going to happen here? So you think, oh my gosh, this is horrible. But what we're going to be able to do here is under this radical, this is actually going to be a perfect square. All right? Acacia's going, oh no. Look at this thing here. Okay, first of all, this is a 4x squared, so we can start with a 2x. What are we going to need over here? What two things together that are the same will multiply to give me 1/64x squared? 1/8x times 1/8x. All right? And look what happens here when we multiply this by itself again. This is 4x squared. I have a 2, this time I have a positive 1/4. The x's are going to cancel out for the middle and the outer terms again. So I'm going to have a plus 1/4 and a plus 1/4. And then I square my 1/8x's together and I get 1/64x squared. So guess what? This then, of course, is equal to this thing here. The 2 1/4 add up to a 1/2. So what happens here, and this is exactly what's going to happen with the homework, is that this whole thing under the radical, it's going to be ending up being a perfect square. So when you take the square root of a perfect square, what am I going to come up with then? So this is then going to be equal to the square root of 2x plus 1/8x squared times itself. So what does that end up simplifying to? Yeah. So now we have something reasonable to work with. So that whole thing, this whole square root of 1 plus the derivative squared, that we started with right up here, I was able to get I get a perfect square under that radical, so that whole thing simplifies to this. So therefore, this 1 plus the derivative squared, the square root of that, now it just equals these nice 2 terms. And this is what we take our integral of then. So we go from x, so we do our x values, x equals 1. Now remember, we're doing an arc length function, so our top value is just going to be the variable x. And then we have our derivative here. Now here, I'm going to do the dummy variable thing again, although you don't have to do that. So instead of writing 2x plus 1 over 8x, I'm writing it as t. But a student in my differential equation class yesterday said, well, why are you doing that? And you don't have to do that, all right? It just is the way you commonly see it written. You could have just kept the x, all right? So that you don't get confused, because the x is some value that varies. The variables in here, when you integrate, those variables in there, they are not constants. It's basically summing things up. So it's just to kind of make it clear that this is x, and these are not the same as that x, okay? So it's what we call dummy variables. They're kind of stand-ins. I could have used anything. I could have used the letter h or any other value, any other thing. But you don't have to. It just helps to make things clear, perhaps. If you get confused by it, then just don't use them, all right? So what's the antiderivative of 2t? T squared, yeah. 2t squared over 2, it's going to be t squared. And the antiderivative of 1 over 8t, one 8 times the natural log of t. This is 1 over 8 times 1 over t. So it's 1 over 8 ln of the natural log of t. Actually, it's the absolute value. We okay with the antiderivative? And then it goes, our limits then are 1 on the bottom, x on top. Okay. So let's plug in. Sandy, are we okay with what I did there? So we plug in the x variable up here. And Susan. Yeah, all right. It started with the right letter of the alphabet. Sorry. Okay, we plug in our top one, so that's going to be x squared plus 1/8 ln of x, all right? And then we subtract and we plug in our bottom one, so that's going to be 1 squared plus 1/8 times the ln of 1. And so this all simplifies to x squared plus 1 over 8 ln of x minus 1, and this, of course, ln of 1 is 0, so that goes away. So this is our arc length function that is our answer then for that, okay? This stuff here is the tricky part, but you're going to want to look for that perfect square under the radical, and all these problems all work out. They're all kind of geared, I think, to work out very nicely where that can simplify under the radical, okay? All right, any question on just computing that arc length function using our formula? So notice the way I did it, and I think that this is helpful. Just start out getting your derivative, then square it, then get your derivative squared, then figure out what the square root of 1 plus that derivative squared is, get that all done, See how you can simplify it with a perfect square. So I do it kind of stepwise, and then I evaluate my integral from there, all right? It makes life a lot easier rather than trying to do it all in one kind of step, all right? Okay. All right, so that's that section. Let's get started here a little bit on the next one. We're not going to go the full length here today, but let's just get started on this. The next section is 8.2. And with 8.2, what we're doing is this. We're taking a curve, and we're going to rotate it around an axis to get a surface. And I'll show you, I've got a PowerPoint with that. So what we're computing is we're computing the area of what's called a surface of revolution. Okay. And from Calc 1, you did things with volumes where you were rotating something around and you got like a solid disk of some kind, and you either used, what was it, the disk method or the cylindrical shell method, right, for calculating the volumes? Do we remember the disk method and the cylindrical shells? Yes, we do. Yes. All right. So anyway, so we're rotating a curve around either the x-axis or the y-axis. Okay, so let's get some kind of picture here for this. And here. Here. Oops. Ooh. Here. So, let's begin. All right. All right. So here we've got, basically, we have a curve. Here's the curve, say right here, or here's the curve right here. Okay, either one. We're starting off with a curve. And in this case, we're revolving this curve around the x-axis. And in this case, we're taking our curve and revolving it around the y-axis. All right, so we could do either one or the other. And what we end up having then is this, it turns out to be some kind of, look like a bowl or a base that's tilted over or whatever. And we have this surface area here that is developed by revolving that whole thing around. Okay? Right? What we're trying to do then is we're trying to figure out, well, what is the area of this surface area that we create by revolving the curve around, all right? So one thing I want to point out here with this, let's look at this one on the right-hand side. First of all, we basically take a slice and we use the formula for the circumference of a circle, because this is revolving around, we get circles. So the circumference of a circle is diameter times pi, right? Or 2 times pi times the radius. All right? In this case, when we revolve it around the y-axis, where's my mouse? The radius here is the x value of the curve. That's our radius. And so the whole circumference of that circle is going to be 2 pi times the x value, 2 pi times the radius. all right? And then we're going to be multiplying that area by a little segment of the curve that we're going to call ds. What we do is similar on the left-hand side. This time we're rotating the curve around the x-axis, so we get these vertical circles. Again, the circumference of the circle is going to be 2 pi times the radius, but in this case, the radius, because it's going around the x-axis, the radius is the y value on the curve. So the circumference here is 2 pi y if we're rotating around the x-axis. Otherwise, it's 2 pi x if we're rotating it around the y-axis. Is this making any sense? Right. Okay. So let me take from that. That down there. That there. And that there. All right. Okay. So finally, I finally mastered how to work this whole thing after a couple months. All right. Yes, I know. Thanks. Got it. All right. So let me try to draw one of my wonderful pictures here. So let's say here we're wanting to rotate a curve around the x-axis. Rotating about the x-axis. So let's say, so this is y, this is x. So let's say we have some kind of curve like this. So this is, okay. And we're wanting to rotate it around, so it's going to be circles. Ooh. I need to be in that class right next door. Circle. And let me first try to draw the mirror image of, so this curve is going to go, it's going to go up and then down and up like that. It's going to look like that. Well, that's not too bad for me. And then we're going to have a circles here, all right? So the whole thing's being revolved around the x-axis. Now, let's take a little slice here. We're going to call this ds, like delta s. Delta s, remember, is the S is the length of the curve. This ds is like a little tiny infinitesimal length of the curve. And then that gets rotated around. So we have this little tiny band, and it also gets rotated around the back of it too. All right. That little slice there gives us a little slice of the whole area of this new surface, all right? So the area of this slice is equal to this. It's equal to that width that I'm going to call ds times, I'll put a dot there, times the circumference of the circle. Times the circumference of the circle. Okay, and so this is equal to ds. In this case, our circumference is going to be 2 pi. Now, because we're rotating it about the x-axis, it's 2 pi y. So another way I can write this area of this slice is 2 pi y, and then put the ds last. All right. Okay. Now, we can do the same thing then if we rotate it around the y-axis. We can do a similar thing. So let's see what this drawing ends up looking like. So let's take some kind of curve. I'm going to keep this one simple. Let's look at a curve like this, all right? And we're going to rotate it around the y-axis now. So our mirror, let me draw the mirror image. It's going to be something like that. Okay, well, something like that. And then we're going to have this big kind of circle thing around as we rotate this around the y-axis. All right. Now again, I want to take a little slice of that curve. We're going to, again, that's going to be our ds. And we're going to have this slice then. So it's going to go around here. And then it's also going to circle around in the back where we have that slice going all the way around in the back. And again then, the area of that slice is going to equal ds times the circumference of the circle. And that's going to be ds times, now how would I now that I'm going around the y-axis, how can I write the circumference of that circle?
2 pi x.
Yeah, 2 pi x. And so this can then be written as, just write it as 2 pi x times ds. All right. So either way, we figured out a way to get the area of a little tiny slice of this total area. So just like you did in Calc 1, when you were figuring out the area of a curve, you basically add all these together and you get an integral. All right? So what we have then is this. Thus, the total surface area is going to equal the integral of 2 pi y ds. This is if we're rotating about the x-axis, if rotating about x-axis, or the integral of 2 pi x ds if we're rotating about the y-axis. All right. Look here at this handout. That's what I have right up here in this top box. I've got 2 columns here. One for if we're rotating about the x-axis, the second column for if we're rotating about the y-axis, all right? And so if we're rotating about the x-axis, this is the general formula for our area, and similarly if we're rotating about the y-axis, okay? All right. Now, I think basically we'll end kind of with this. We'll do some examples, I think, on Monday. But the last thing here that we want to point out. Okay, so here, notice in both of these integrals we have ds. All right. Now, in the previous section, we developed 2 formulas for the ds. So this is from section 8.1. We had that ds is equal to the square root of 1 plus dy dx squared times dx, or ds is equal to the square root of 1 plus, here I'm interchanging the x's and the y's, dx dy squared dy. Now, we're going to use this one if our curve is something like y equal a function of x. We're going to use the one that has the dx in it. If our curve is x equaling a function of y, the other way, we want to use the dy. All right? Okay. So let's kind of look here then at the final result here with this, and it's on your sheets there, but let's put it down here. All right. So if we have two cases here. One where we're rotating about the x-axis, and the problems in the homework will clearly state x-axis or y-axis, okay? Or the other case if we're rotating about the y-axis. Oops, how about putting y? How about the y-axis? Okay, remember, if we're rotating about the x-axis, the general thing is going to be 2 pi y ds. If we're rotating about the y-axis, it's going to be 2 pi x ds. That's our general format. Now, in each of these, we have two possible cases. One is the case where our curve is written as a function of x. The other case is if our curve is written as a function of y. So under each of these, we have two cases. The first case for each one of them is this. The curve is written as y equal a function of x, and it'll tell you the values of x that we're going for. So let's just say x between a and b. And that's the same case that we have over here. For the first case, the curve is written as y equal a function of x for x going from a to b. All right. Now, with this one then, we're going to have our dx is going to be equal to this format right here. The square root of 1 plus dy dx squared dx. We're going to want to use that one. Okay. So therefore, I just plug this in then. I've got my formula, basic formula for rotating about the x-axis. So now my formula then is going to be from x going from a to b, 2 pi. Now, what we're going to want then is x's here in our integral. So I'm going to write the function of x that it is equal to f of x times my d of ds, which is going to be 1 plus dy dx squared dx. Okay. So this all looks potentially horrible as far as getting antiderivatives of, but you're going to find in the problems that you've got that lots of things cancel out, and the antiderivatives aren't bad. All right? Now, in this case here, let's go back here to rotating about the y-axis. Okay, our curve in this case is written as a function of x, so it's the same ds formula that we're using. So it's going to be the same thing where we're integrating from a to b. All right? But this time, remember what our formula is. It's 2 pi x times dx if we're going around the y-axis. So now this would be 2 pi. I wouldn't write f of x. I just write my plain old x. And that's what I have here in the handout. Keep it as plain x. And then I have my 1 plus dy dx squared dx. That's my ds formula. All right. So the difference here is that here if we're going around the y-axis, it's 2 pi x. We just keep it like that. The other one, we have to write the f of x. We want a function of x. One case is a little bit easier than the other. Then the second case then here is if the curve is written as x equaling a function of y. and therefore we would say we would be given the limits for the y going from, say, C to D. And then we use our same formula that we have up here. So notice our formula up here, we're rotating here about the x-axis. So it's 2 pi. We're going to want to use the y here because we want to have a function of y. But we're going to use for our ds, we're going to use this formula here. We're going to use ds equal to 1 plus dx dy squared dy. We want to have the dy, so we're going to have 1 plus dx dy squared dy. And y is going from C to D. So notice what we end up with here is all y. Okay? And then the thing is here, if the curve is, again, if it's, in this case, if it's x equal to g of y, it's going to be, again, from C to D, but this time it's x. So I'm going to put 2 pi, but instead of the x here, I'm going to put my y formula, g of y, and then times my ds formula, 1 plus dx dy squared dy. And again, this is going to end up being all y's for my, in my integral, right? So we have these various cases. I think the handout here pretty much sums it all up, okay, the different cases we have, and I hope it's helpful. What we're going to then start with, we'll stop. What we're going to start with the next time then is we're going to do some examples of this.